Hello everyone! In this tutorial, I'd like to return to simple effects that don't require any image input. This time, we'll create something like an animated nebula, which can be an interesting visual enhancement for many space games. So, let's build it. So, as I said, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background. So I'll create a new scene and set everything up. Okay, scrolling up, something is open here. Right-click into the scenes folder and create a new scene, which is this time user interface, and let's call it Stormy Nebula. Sorry. Check keyboard once again, Stormy Nebula. Okay. And right-clicking the root node, add child node, colorrect, where I do some changes in the inspector, like changing the background color to black, opening layout, transform, and I'll set the full HD resolution 1920 by 1080. Okay, scrolling down to the material section, creating a new shader material, click it and create a new shader. Type shader, mode canvas item, the name Stormy Nebula GD shader, and I put it to the shaders folder. Create and click again to open it in the shader editor. Okay, and as always, I'll delete everything that we don't need for our effect, leaving only the fragment function. Deleting vertex and deleting light. Ctrl S to save. Okay, so this time we don't have an image available from which we could determine the resolution. So instead, I'll add a uniform parameter to define it. And as we could see at the beginning of the video, this will be an animated effect. So we'll also add a parameter to define the speed of this animation. Let's do it here. Uniform vec2 resolution equals, the default value is 1920 and 1080, our full HD resolution, and a uniform float speed with a hint range and initial speed let's set to 1, and it can go from 0 to, for instance, 4 with the step point 01. Okay, and we can write the basic version of the fragment function. This effect we are creating will be symmetrical around the center. So I'll start by shifting the origin of the coordinates to the center. Because we are working with UV coordinates, that is, in the range from 0 to 1, it's enough to subtract 0.5 from the UV variable. So let's delete this comment in the fragment function, and I'll write vec2 UV equals UV minus 0.5. Okay, next we want the effect to look the same regardless of the dimensions of the element, in our case the colorrect. So I'll recalculate the aspect ratio using the usual formula. uv.x is multiplied by resolution x divided by resolution.y. Okay, let's continue by defining a time variable. As we know from previous tutorials, it will depend on the internal time and the speed parameter. Float time equals time times speed. Okay, and because we are working with the fractal structures that can be scaled up and down, a parameter for adjusting the zoom factor will be definitely pretty useful. So I'll add it as well, scrolling up to the material, to the section of uniform parameters and uniform float zoom with a hint range and the initial zoom. Let's set to 5, and it will go from 0.1 to, for instance, 20 with the step point 01. Okay, and I'll insert the corresponding line into the fragment function just before the time definition. Let's do this. UV is multiplied by zoom. Okay. We still have one more UV coordinate transformation prepared, but we'll get to that shortly. For now, you could say that we have the basic version of the fragment function ready, and we can continue by implementing the helper functions. To generate those jagged and glowing lines you could see at the beginning of the video, we'll need a pseudorandom vector generator, which is nothing new to those who have been following this channel for a while. This time, I decided to recycle the so-called simplex noise, whose implementation I described in the tutorial about creating a waterfall effect, and from which I borrowed the code in question. It turned out that this algorithm is very suitable thanks to its finer grain and triangle-based structures, which stand out better in effects like these. So, to avoid writing too much code manually, I'll paste the prepared code and then briefly describe it. Okay, so let's expand this window and I will paste it right after the uniform parameters. Okay, so first, I added a uniform parameter called octaves, which defines the number of iterations that we will need in the final calculation. Then we have these constants S and U, which stand for skew and unskew factors belonging to the simplex noise algorithm. I turn them into constants so we don't have to perform this calculation separately for every pixel. Next, we have the standard pseudorandom vector generator, also used in many earlier videos. After that comes the noise function, which implements the mentioned simplex noise according to the algorithm, whose detailed description can be found, for example, on Wikipedia. And for calculating the final structure, we use the usual algorithm called fractal Brownian motion, meaning the accumulation of results over several iterations with different parameters. Again, the exact description of this algorithm can be found in external resources such as the Book of Shaders, which I mention every time and also link in the video description. So we can return to the fragment function right here, where I'll perform the final promised UV coordinate transformation, namely according to the result of the FBM function we just added. It will look very simple like this. So right after UV is multiplied by zoom, let's add this. UV is increased by plus equals FBM of UV vector. Okay, the algorithm behind our effect will be based both on deforming the UV coordinates and on emphasizing individual structures depending on the distance of current pixel from the origin of the coordinates, that is, from the center. So we'll start with the deformation, which we already introduced through the call to the FBM function, and now we'll animate it further using trigonometric functions. We'll have a total of 4 color shades, and for each one we'll use a different combination of sine and cosine functions with different constants to vary the frequency. In practice, it will look like this. Okay, so I'm adding new lines to the end of the fragment function, and let's start with the first one. Vec2, and let's call it A for simplicity, is UV plus Vec2, and now the trigonometric function sine of time times 1.5 in the sine of time times 0.9, for instance. Okay, so this is the first line, and now we'll copy and paste it 3 times and do some changes in this coefficient. So 1, 2, 3, and I'll rename them to B, C, and D. Okay, and now we want to change these multiplications. Basically, they are arbitrary numbers, but I just selected this one, 1.7, 1.9, and 2.1. And as for the second part, 0.9, 1.9, 1, 1.3, and 1.5. Okay, and we also want to alternate between sine and cosine. So here we have sine and sine. The second line will be cosine and sine. The third line, sine and cosine. And the last one, two cosines, just to give it some diversity. Okay, and now I mentioned four colors, so now I'll add four uniform parameters so we can easily fine-tune the appearance of the effect. Scrolling up, and here in the uniform parameters section, uniform vec3, just RGB color, let's call it color A, with the hint source color, and the initial value I'll set to vec3.5, which is a shade of gray. All three components are the same, and now we can simply again copy and paste 3 times and create color B, color C, and color D. And here I think I had a little bit different default values. So for color B, let's make it 0.5, 0.2, and 0.1. The third one, color C, would be just white color, 1. And the last one, 0.6, 0.4, 0.1. You can select any other colors and of course change them in the inspector later. I think I'll just open that here because we need to reset the default values to reflect these changes. Okay, and what does the pixel color calculation look like? Very simple, because it's just a matter of dividing a specific color by the length of the corresponding vector, like this. So scrolling back to the end of the fragment function, and I will add this line. Vec3 color equals color A divided by length A. Okay, that's it. And now I think I'll put it to the next line. So it is just better formatted. Color B divided by length of B. And the same for C and D. So copy and paste twice. Color C, color D, and here length of C, and the length of the vector D, and semicolon. Okay, so now we have some vec3 color which we can display. Let's do it, and I will show the 2D editor so we can immediately see the result. And the last line so far will be the output variable. Color in capital letters equals vec4 of color and 1 for the alpha channel. Okay, so this looks more like some kind of a supernova, I guess. The colors are heavily overexposed because of these accumulations. So we need to tone them down a bit. I'll add one final uniform parameter called contrast. Let's scroll up again, and right after the color parameters, I will add the uniform float contrast with a hint range, and let's set the contrast to 2, and it goes from 0.01 to, for instance, 10 with the step 0.01. Okay, scrolling down, and right before displaying the color, let's add this. Color is divided by contrast. Wait for it. Okay, that's better. And when I increase the contrast in the inspector, we also get the expected animated lightning-like streaks. Let's try it out. Here it is, increasing. Yeah, I would say it looks pretty cool. Okay, still, I think it could use one more adjustment, namely the application of so-called Reinhardt tone mapping, like this. So I'll reset the contrast to the original value, and just before the color in capital letters, let's add the adjustment. Color is multiplied by 0.8 divided by 3.5 plus color. Okay, and here we go. This is definitely easier on the eyes. Of course, if our game supports high dynamic range, we can omit this line. Very well, what's left? Someone might want to display such a nebula with a transparent color instead of black, so the effect can be used over a different background. We've already done this several times before, and the trick lies in defining a threshold for changing the alpha channel from 1 to 0. So I'll add one more uniform parameter. Okay, scrolling up, and here I will add definitely the last uniform parameter, uniform float. Alpha threshold with a hint range, and the initial value, I think it's 0, okay, and the range goes from 0 to 1 with the step point 0, 1, scrolling down to the end of the fragment function, and now dimension adjustment based on the average value of the color components. So it will be float avg for average is color.r plus color.g plus color.b and divided by 3, so it's an arithmetic mean. And here the color is vector 4 color, and instead of just 1, I will write this ternary operation. So avg is less or equal to alpha threshold. If it is, let's make it transparent, otherwise let's make it opaque. Okay, and let's try it out in the inspector. So increasing, and yeah, something is definitely going on there. It looks like this nebula may not be entirely suitable for the techniques like this, but perhaps by playing with the contrast we can achieve something usable. Let's decrease the contrast, and yeah, we got some very interesting animated blobs. Okay, it can be useful or maybe not, it's up to everyone. Let's reset the values and just have a look at the original effect. Thank you very much for watching. I think even simple effects like this one can find their use, especially if we experiment with the color settings and control the speed, zoom and contrast directly from the game. And of course, we can also experiment with changing various constants or replacing simplex noise with a different algorithm. As usual, there are plenty of possibilities for additional refinements. In any case, take care, good luck with your projects, and I'll see you in the next video.